Okay, so we're still doing section 7.2, and we're going to start now with a summary of what we saw in a bit more detail in the last video. So summary here. This is a summary for calculating a confidence interval for the population mean mu x. So suppose we're investigating a random variable x with unknown parameters mu and sigma. We decide to do a sample of size n, and we get sample statistics x bar and s. So to do this method, the requirements are the sample has to be a simple random sample, SRS. All of statistics assumes that it's a simple random sample. In reality, it usually isn't. There's a kind of a conflict, a sort of a tension between statistical theory and real life practice. But formally speaking, it has to be a simple random sample. Second thing, either or both of these conditions must be true. X must be normal, or the sample must be large enough, at least 30. Then what we do, if we want a confidence level of 1 minus alpha, then, or using a confidence level of 1 minus alpha, we know that the population mean is between the sample mean minus E and the sample mean plus E, where E is the margin of error. It's called the margin of error, and it's given by this formula where where the value t alpha over 2 is the critical t value with an area of alpha over 2 to its right. So that's the area alpha over 2 to the right. That's called the critical t value. And this has degrees of freedom is n minus 1. So we calculate it using either a table, there are tables in your book, which is kind of the old-fashioned way, or we can use something like Excel or other tools. In Excel, it's going to be 1 minus alpha over 2 n minus 1. Okay, and then this value is the same, it's just negative. Okay, now this is a bit misleading because it makes it look like the area, this distribution it's a t distribution. with degrees of freedom equals n minus 1. And again, why is it called degrees of freedom? It doesn't really matter. We're not going to get into it. It's just a funny name for the fact that it depends on n. Okay. Now, once we get this interval, we will want to round it off somehow, right? So there's no ideal answer here, but the convention is that if we're working with a data set, like a list of numbers, then we'll use one additional decimal point in the confidence interval. If we're working with sample statistics, like if we're just told x bar and s, then we use the same number of digits as in x bar and s. But if we're given the data, the raw data, then we use one more decimal point, use one more digit. One more than what is in the data. Okay, and why is that? It's there's no deep reason. Again, it's mainly a convention that makes sense. Okay, so that's the summary, and now we can use it in a kind of another realistic example. So we did the birth weights of boys in the last video, sorry, of girls. Now we're going to look at the birth weights of boys. So using the summary statistics from the data set that we were looking at, the mean for boys is, now they read it in a strange way. They use this symbol HG, which means hectograms. So hectograms would mean hundreds of grams, but I think it's very strange to use that. So let's just change it to regular grams. That's fine. And the S is 6.6 hectograms, which is 660 grams. Okay. Okay, Hg. Who's ever heard of that? Maybe it's normal in medical things, but I've never used that. Now, we're going to use a 95% confidence level. So we're choosing alpha is 0.05, which means 1 minus alpha is 95%. So what do we need to do? We need our t value. Our t statistic is t 0.025, and we'll get that from Excel. 1 minus alpha over 2. Good. 1 minus alpha over 2. And the degrees of freedom was, well, how many boys were there? 195 boys. I thought it wasn't there for a second. 195 minus 1. And what do we get? Let's see. I can do it in here. We're not going to use the data because we're told the, we could check it though. What's the X bar for boys? It's going to be the mean value from the 207th row, I guess, which is when the boys start. The boys started at 207 down to 207 down to 207 to 401. 207 to 401. 207 to 401. So the X bar for boys is average of G207 up to G401. 3272.8. What did the question say? 32.7. Okay, so they've rounded it off. That's fine. Oh yeah, we were calculating the t. So the critical t value is going to be equals t dot inverse 1 minus 0.025, 195 minus 1, 1.97226. So that's slightly different than the t from the girls. The t from the girls was 97166, 1.97166. This one is 97226. Why is it different? Because it's a different n. Not that different though. So the margin of error is t alpha over 2 times s over the square root of n. 1.97226. S is given, 660. Square root of 195. What do I get? I'm going to calculate it here. This is K11 times the S value, which is 660, divided by square root of 195. 93.216. 93.216 grams. So now the 95% confidence interval is going to be from X bar plus E, from X bar minus E up to X bar plus E. So what is that? 3270 plus 93.216. 3270 minus 93.216. What are those numbers? X bar minus E, K10 minus E is K12 x bar plus e, k10 plus k12. 3366.0. oops, I put it in the wrong spot. 3179.6. This should be here. This is 3179.6. Okay, so now we need to round it appropriately, right? So we need to round it so that it has the same number of digits as the given sample statistics, which was well, it depends. This one has 3, this one has 2, but I'll show you and then I'll tell you. So we're going to round it to keep these 3 digits and keep these 2 digits. I take that back, just to keep the first 3 digits. So it becomes 318,337 grams. Okay, so that's our confidence interval for the boys. Now, forget this part, because we didn't do exercise 9. Does it appear that boys and girls have very different weights? Well, let's think here. So if we put both the confidence intervals on a number line, then let's put the boys here. The boys, I know they'll be a little heavier, or maybe they won't be heavier, right? Let's see. Let's just put it 3180 up to 3370. That's the range. That's the interval for boys. What was the interval for girls? Let's go back and get that one. We did that before. 2940, 3130. 2940, 3130. 3130 is actually less than that. So now I regret making this so big. Let me shrink it a little bit. I regret that. So if I'm surprised actually. I would have thought that the at birth there should be not much difference between the boys and the girls. So what does that mean? Did I read it wrong? 3130. Did I read it wrong? Let's see. Nope, that's the upper limit. 2940. That's for girls. 2940. 2940. This is for girls. And so it looks like they don't overlap. The intervals do not overlap. So what that means is that the mean, our best estimate of the girl's weights, let's call that girl, is within its own interval, and the best estimate of the boys is in its own interval. So that what that means is, informally speaking, we can say that we are confident that that mu girl is going to be less than mu boy. Because to be greater than mu boy, it would have to actually be somewhere in this, it would have to be somewhere in this interval, and this would have to be somewhere in the lower end. But that's not going to happen because, well, it could, but it's most likely that mu girl is somewhere in this lower interval. So we're confident that there is a difference. I find that surprising. Very different. Is it very different? I'm not sure if it's very different, but it's different. Okay, so we'll do one more example like this, and then we'll take another break. Okay, so Now, what's going on this time is we have a fairly small sample, and that reminds me, on the boys and girls, did we ever check anything about the sample size? We didn't. That's kind of bad, isn't it? We should have checked something. What we should do is right here, we should check, before we do anything, we should check, are the requirements met? Is X normal? No, we don't know. But is the sample size greater than or equal to 30? Yes. So we're fine. I didn't check it because it's kind of obvious, but we do have to include that. Okay, so now for this one, we're going to make sure we do the requirements right at the beginning. Okay, what is the question? Years in college. Listed below are the numbers of years it took for a random sample of college students to earn bachelor's degrees. Construct a 95% confidence interval estimate of the mean time required, so the mean would be mu x, the mean time required for all college students to earn bachelor's degrees. So some of these students graduated in 4 years, and these ones are 4.5. But there were a few people who took 15 years. That would be definitely an outlier, right? That's a long time to get your bachelor's degree. Does it appear that college students typically earn bachelor's degrees in 4 years? Is there anything about the data that would suggest that the confidence interval might not be a good result? Well, what do we do here? We're going to do the requirements in just a second. Let's start by recording some of the sample info, sample data. So what we'll do is I'm just going to type these numbers into Excel, and I'll take a short pause while I do that. And so I've got the variable X here, the years in college. I've typed all the data into columns. So I've got 6 4s, 6 4.5s, a couple of 6s, 8, 2 9s, 2 13s. There's the 15. So I've got 20 data points. So let me write my sample statistics over here. N is 20. X bar is, let's see, it's going to be the average of A2 up to A21. S is stdev.s A2 up to A21. And N is 20, so that's not very big. So we should keep that in mind. N is 20. X bar is 6.5. And S is 3.50563. 3.50563. So to proceed here, to carry on with the procedure, we need to know that either X is normal or N is greater than or equal to 30. Well, I know that N is not greater than or equal to 30. It's only 20. Is X normal? Well, now we need to use our skills from section 6.5. So how do we know if it's normal? Probably the best thing to do is just throw it into a histogram. So I'm going to select all these. That 15 is worrying me. But how does it look if we make a histogram? So we'll go down to histograms. Uh-oh, and it looks not very normal, right? So, but maybe it's just because I have 3 bars, only 3 bars. So I could probably make it, what's the square root of 20? It's only 4 point something. I could bend that a little and make it 5. So let's make it 5 bins. That looks even worse, right? So that looks like a very non-normal variable. So a histogram of X equals number of years in college. This is for a sample of 20. So I'm going to just copy and paste this into my other notes just so we have something to look at. X in years. So I'm not going to do a normal QQ plot because I'm already pretty sure this is not normal, right? This is frequency. So I'll copy and paste this. And so officially, we should stop here, right? Officially, we can't use this method because the central limit theorem doesn't guarantee us that X bar is normally distributed. None of the rest of it works. Now, typically what we do in stats is we say, okay, well, I know I shouldn't go on, but I'm going to go on anyway and see what happens. So let's see, let's do that. We know that we are operating without a safety net here. Let's see what happens. So this is non-normal, right? It looks highly skewed. We're going to carry on anyway. So what that means is that we have to treat our results with extreme skepticism, right? We have no confidence, we have no reason to think that they're applicable. We'll see what they say. So what do we do next? We calculate the critical t value, which is, well, what is alpha anyway? Alpha is constructing 95% confidence interval. So we have alpha is 0.05, which means 1 minus alpha is 0.95, which is what we want. So then the critical t value is going to be t dot inverse 1 minus 0.025, which is half of alpha. The n is, the degrees of freedom is 20 minus 1. So what do I get? This is going to be quite a large t-value because it has a small sample size. T dot inverse 1 minus 0.05 divided by 2, 20 minus 1. So a large t, 2.09, 2.09302. Okay, now what's my margin of error? Is critical t times s over square root of n, 2.09302. S was given, n is 20. What do I get? Let's do it on this calculator. 2.09302, 3.50563, square root of 20. Margin of error is 1.6406. Okay, so now what is my confidence interval? It's going to be x bar minus the margin of error, x bar plus the margin of error. X bar was 6.5 minus the margin of error. X bar plus the margin of error. So let's see. So if I do plus 6.5, I get 8.14. And remember that I'm going to be rounding this off to be the same number of, no, I take that back. We're going to be matching the number of, what am I saying? Now, this is interesting. So these data are given with not very many digits, but these are actually very precise, right? Because if you take 4 years, it's exactly 4 years. If you take 13 years, it's exactly 13 years. So the rounding is a little bit ambiguous here. So let's actually use the, let's assume that these all have one more digit after the decimal place. Since some of them have 0.5, we'll assume that they all have a point something. In other words, they have one digit after the decimal point. So we're going to add one digit after the decimal point. we're going to add 1 digit. So and here I'm going to do 6.5 minus that number. So I get 4.8593. And finally, I'm going to do my rounding here. So I'm adding a digit after the decimal point. 86. So that's my confidence interval for, it's a 95% confidence interval. Sometimes we denote that just CI for the mean number of years it takes to complete college, to complete a bachelor's degree. This is an estimate for the entire population. What is the population here, by the way? It's probably all US students, right? Yeah, so I don't know where these data come from, but it's for, now, does it appear that college students typically earn bachelor's degrees in 4 years? No. It looks like it typically takes more than 4 years. Now, I want to make a bit more space here. Okay, so it appears that completing college in just 4 years is relatively unlikely. Is quite unlikely, right? Because it's outside of the interval. Since 4 is outside of the interval, it's too small. But that doesn't make any sense, right? Because plenty of people completed it in 4 years. In fact, that was the most common number, tied with 4.5. 4.5 is also outside of the interval. So 12 of these people are actually outside of the confidence interval. Now that doesn't make sense. So what's wrong with this? Is there anything to suggest that anything about the data that would suggest the confidence interval might not be a good result? So this result is inaccurate. It is useless because the non-normality of the original data, made the method that we used inapplicable. It wasn't an appropriate method to do, and so we got a nonsense result, which says that 4 years, 4.5 years shouldn't happen very often. That's not the average. But we can see that the mean is probably very close to 4. Okay, so we do have to check the requirements and proceed appropriately. If the method is not applicable, we should report that as our answer and maybe possibly try to find a more advanced method that will work in that circumstance. All right, so we'll leave it there. The last video, we're going to be doing sample size determinations. All right, see you then.